Welcome back, guys. In this video, we're going to talk about conservative force as well as conservation of mechanical energy. So first of all, what is a conservative force? In fact, a conservative force is any force where the work done by this force depends only on initial and final positions. It doesn't depend on the path followed from the initial to the final position. The first example on a conservative force is the gravitational force, the weight. If I want to find the work done by the weight between A and B, then I have to say that this work W or this work U is equal to minus the weight times delta Y, which means it is minus the weight times YB minus YA. If I remove the sign with YB minus YA so that it is the weight times YA minus YB, which is a positive term, then this will be W times delta H. Alright, so let's take an example. Assume that the weight is 10 newtons and delta H is 2, then the weight between the work between A and B done by this weight will be equal to 20 joules, right? So U will be equal to 20 joules. Now, assume that this weight here at A is going by downward by 2, then upward by 2, then downward again by 2. What do you think will be the work of this weight? In this case, guys, the work of the weight will be equal to U1, which is the downward path, plus U2, which is the upward path, plus U3, which is the second downward path. Now, what about U1? It's also minus W YB minus YA, which is also W times delta H, and since delta H is 2, and since the weight is 10, then it is plus 20. It should be plus because in fact this motion here is with the weight. Now what about the upward motion? It is minus 20. Now what about the downward motion again? It is plus 20. Which means, guys, the final answer is 20. Which is the same as this answer. What does this mean? If the path followed between A and B is curvilinear and it's downward once between A and B, the answer is 20. If the path followed between A and B is rectilinear, going downward, upward, and then downward between A and B, then also the answer is 20. So if I have to position, any path followed by these two positions will give me the same work of the weight. And that's why I can call this force, the gravitational force, the weight, as conservative. Another example of conservative force is the elastic force. Why? Because as you remember, guys, from the previous video, I know that the gravitational force that the elastic force has a work of half K, which is the constant of the spring, S1 squared minus S2 squared. Which means, guys, it only depends on S1 and S2. It doesn't depend at all on the path followed by S1 and S2. For example, if I take this one here, and I'm going to assume that this spring is, or this body here is going to the right between XA and XB, and I want to find what is the work done by this elastic force between XA and XB. This work will be half K S1 squared minus S2 squared, where S1 will be XA minus X0 and S2 will be XB minus X0. Now, what if this body here is going to the right, then to the left, then to the right, always between, it's going to the right, then to the left, then to the right, always between XA and XB. You're gonna have, in fact, the same answer because it's always a function of S1 and S2 regardless of the path followed between XA and XB, and this means that the elastic force is also a conservative force. Now, why is it called conservative? Because a conservative force conserves the mechanical energy. What is a mechanical energy? A mechanical energy at a certain time or at a certain position is the sum of the potential energy and the kinetic energy. And we're going to talk later on the potential energy. Now, what if I have non-conservative force? A non-conservative force does not conserve mechanical energy. In fact, an example of non-conservative force is the frictional force or the resistance of air. The frictional force will never conserve the mechanical energy. If I have a system of frictional force, the mechanical energy will not be conserved. Instead, it will be decreased. This mechanical energy, a percentage of this mechanical energy will be transferred to a thermal energy due to the presence of this frictional force. And what you have to know, guys, is that the work of a frictional force always proportional to the distance traveled. I want you guys to remember the difference between the distance traveled and the displacement from the first part of this course of chapter 12. In fact, guys, the distance traveled depends on the path followed, while the displacement is only the difference between S2 and S1. And since the frictional force, the work of the frictional force depends on the distance traveled and not on the displacement, then this is not a conservative force. It depends on the path followed. For example, guys, if I have a body that is moving to the right, then to the left, then to the right, this body will have a work done by the frictional force much greater than the work done if this body is only moving once to the right. Alright? So the path, guys, followed, the distance traveled by this body or by this particle is gonna affect the work of this frictional force. Alright? So always, guys, the work of the frictional force depends always on what? It is proportional to the distance traveled, right? So guys, if this body is going to the right once, it will have a certain frictional force that is much less than if this particle is going left and right, back and forth multiple times. The thermal energy will of course be increased here, alright? So if you do this frictional force once, you're gonna feel your hands a little bit hot. But if you do this, and even if you're gonna conserve the final position, then the frictional force will make more work, and then you're gonna feel more thermal energy. Your hands will be hotter. Alright? So this is for the frictional force. It's not a conservative force, and the same case for the resistance force. Now, if this is not a conservative force, then the mechanical energy will not be conserved. In fact, it will be lost. A percentage of this mechanical force will be lost in the form of thermal energy. What you have to know now that if I have a conservative force, then I can assign to this conservative force what is called a potential energy V. A potential energy is the measure of the amount of work, the amount of work a conservative force only will do when this body is changing its position. For example, for the weight, guys, it is plus or minus W times Y. Now, what is Y? Y is the distance from the datum. So for potential energy, guys, due to gravity, you should indicate a datum, and then you have to find what is Y. And then, guys, if Y is above the datum, the potential energy of the gravity force at this position will be positive. If it is below the datum, then the potential energy will be negative. What about the elastic potential energy? It's always equal to half K S squared. So it's always positive here. There is no problem in the sign of elastic potential energy. It's always positive because S is squared. All right. So the potential energy for the spring is half K S squared. So now, guys, why should I define this potential energy, and how can I translate it to the conservation of mechanical energy? In fact, guys, between two positions, if I have only conservative forces, then T1 plus V1, which is the mechanical energy at position 1, should always be conserved, which means it should be equal to T2 plus V2. What is T? T is the kinetic energy. And what is V? V is the potential energy. And don't forget, guys, that this potential energy will be the sum of elastic potential energy and the gravitational potential energy. And from here, guys, comes the fact that a kinetic energy could be exchanged by the potential energy, as we're going to see in the problem solved. Thank you.